Okay, so let's continue with part 2 of exercise 2.2. And it's the same setup as before. So, A was 0, 1, 1, 0. A being applied to the 0 vector gives you 1. A applied to 1 gives you 0. 0 is defined like this, 1 is defined like that. And so now the question is, hey, let's find a different basis and find how A is transformed in that different basis. And so we're just going to say, there's a lot of steps here, so it might take a minute, but there's nothing that's, I think, overly complicated. So let's define some vector, call it v1 equals 1 over root 2, 1, 1. And let's say v2 equals 1 over root 2, 1, negative 1. This is absolutely something I can do. You can verify for yourself that these two are orthogonal and they do span the space, meaning any vector in the xy plane can be written as a linear combination of these two vectors. And so we also know that our 0 vector, right, in any vector, our 0 vector can be represented as some weight times v1 plus some other weight times v2, right? And so let's carry that out more explicitly. Yeah, so let's write this out more explicitly. So it's going to be, let's call it alpha over root 2 of 1, 1 plus beta over 2 of 1, negative 1, right? Also notice that if I add v1 and v2 together, so v1 plus v2, I just add these together, so the ones will double up, then the 1 and negative 1 will cancel each other out. So 1 over root 2, 1, 1, plus 1 over root 2, 1, negative 1. And that's going to give us, 1 over root 2 of 2, 0, like this. And because I can pull a scalar out, I'm going to rewrite this as 2 over root 2 of 1, 0. In other words, v1 plus v2 is equal to the 0 vector multiplied by 2 over root 2. So I can rewrite this 0 vector just using some algebra. I can rewrite this 0 vector as root 2 over 2 v1 plus root 2 over 2 v2. I'm just going to erase this to make some room for myself on the board here. Now I can carry through the exact same exercise using the number 1 instead of 0, and it's going to be the same analysis. The only difference here is I am going to get in fact, let me write this as, instead of root 2 over 2, I'll write this as 1 over root 2. It's mathematically exactly the same. It's just, a little more, mathematicians hate it, but physicists like this notation. Don't ask me why. Okay, and that is still the exact same thing as the 0 vector, and the 1 vector can be rewritten as 1 over root 2 v1 minus 1 over root 2 v2. Okay, so the 0 vector can be rewritten as this, the 1 vector can be rewritten as that. Taking it a step further, we can actually redefine V1. So this is just algebra. I'm skipping the algebra. You know, don't skip leg day, don't skip algebra. Well, I'm skipping the algebra. So we can rewrite V1 as 1 over root 2, 0 plus 1. And we can rewrite V2 as 1 over root 2, 0 minus vector 1. Okay. And so what happens when we apply A to V1? So if we apply A to V1, right? So let me use a different color here. So A being applied to vector V1 is the same thing as applying it to this giant thing, right? So A being applied to 1 over root 2, 0 plus 1. But remember, A is a linear operator. That means we can either apply it to the entire vector or we can apply it to the pieces of the vector. So I'm going to apply it to the pieces of the vector. So it's going to equal 1 over root 2 of A0 plus A1. Well, by definition, A applied to 0 is 1, A applied to 1 is 0. So really, this equals 1 over root 2 of vector 1 plus vector 0. Okay. That's cool, but that's really the same thing as that, right? So really, maybe the order is reversed, but addition is commutative, so that doesn't matter. So really what we just found is that A applied to V1 gives us V1 right back. In fact, let's make that explicit up here. So if I apply A to vector V1, I get V1 right back. Okay, and then if we do a similar analysis for V2, what we're going to get is A applied to V2 equals, again, skipping a couple of the steps, A0 minus A being applied to 1, which equals 1 over root 2 of 1 minus 0. Now, 1 minus 0 is kind of the opposite of 0 minus 1. In fact, it's the negative of 0 minus 1. So really, AV2 equals negative V2. AV2 equals negative V2. So let's store that up here. AV1 equals V1, and A applied to V2 equals V2. And then with that, we run through the exact same exercise. So now we want to express A in this new set of basis vectors. And so we just run through the same algorithm that we did before. So A, B, C, D being applied to this new basis vector. So in the V1, V2 space, I can represent V1 as this, right? So this gives me 1, 0. It's just another way of writing A times V1 equals V1, right? And we've already been through this much. So we could say that A equals 0 and C equals 1. That's exactly what we got before. So we're just going to skip that algebra for a second. So now let's do AV2, right? So A, B, C, D, applied to, in fact, let's make the R substitution. So that's a 0 and that's a 1. Being applied to the second, the next basis vector, is going to give us 0, negative 1. Negative 1, right? And so we're going to get 0 times 0 plus b times 1. And then on the bottom, we're going to get 1 times 0 plus d times 1. D times 1. So that means that, so that gives us b and d equals 0, negative 1. So b equals 0 and d equals negative 1. Therefore, in our new basis, our brand new basis, we could say, we can rewrite matrix A as being equivalent to 0, just making sure I got my stuff right. You know, I got my A and C mixed up, so let's do that one more time. So A, B, C, D on 1, 0. Yeah, I got equals 1, 0. Yep, so I'm going to get AC equals 1, 0. Yep, 1, 0 like that. My bad. That's why you got to do the algebra. So at the end of the day, A is going to be equivalent to 1, 0, 0, negative 1 in the basis V1, V2. Ooh, how abstract.